The James Webb Space Telescope recently photographed galaxies that should not exist. Not galaxies that surprised astronomers, not galaxies that required a little tweaking of the models. Galaxies that the entire theoretical framework of modern cosmology says cannot be there. And when John Mather, the Nobel Prize-winning physicist who spent 2 decades building the instrument that certified our understanding of the early universe, looked at the data Webb returned, he said 4 words: "This is not our universe." He did not say it in a peer-reviewed paper. He did not wrap the statement in error bars or methodology caveats. He said it in a public forum, for words. And since he said them, no one with comparable standing in cosmology has publicly refuted him. That specific silence matters. To understand why, you need to understand who Mather is and what he built in the 1990s. Mather led the COBE satellite mission. COBE measured the cosmic microwave background, the faint thermal afterglow of the universe's earliest moments, the radiation left over from roughly 380,000 years after the beginning, when the universe cooled enough for hydrogen atoms to form and light was finally free to travel. His instrument found temperature variations across the sky at 1 part in 100,000, precisely where the standard model of cosmology predicted. The Nobel Committee awarded him the prize in 2006, not for proposing a theory, for confirming one with a precision that left no statistical room for doubt. Mather was, in the most literal scientific sense, the person who certified the foundation of modern cosmology. When you want to know whether the bedrock holds, you call the geologist who measured it. And when that geologist comes back from the field and says the ground is different than the maps show, you do not dismiss the statement. You start asking what the maps got wrong. This is where Webb brought us. And the story of how we arrived at this point runs through multiple instruments, multiple anomalies, multiple teams working independently and arriving at the same uncomfortable conclusion. In February of 2023, a team led by Ivo Lab published a paper in the journal Nature. They reported 6 galaxies that Webb had photographed in the earliest observable slice of cosmic time, existing between 500 and 700 million years after the beginning of the universe. Each of these galaxies contained a stellar mass equivalent to tens of billions of suns. Together, according to Labby's estimates, these 6 objects held more total stellar mass than the entire observable universe was supposed to have. Produced by that point in cosmic history, Mike Boylan-Colchan at the University of Texas at Austin read the paper and used 2 words to describe the galaxies: universe breakers. His analysis was precise about why. To form stars, matter must collapse under gravity. Gravity collapses matter at a rate physics sets, and that rate has a ceiling. There is no physical mechanism that allows matter to collapse faster than gravity permits. The galaxies Webb photographed had apparently done exactly that. They had formed far more stellar mass than the available time and the available gravitational dynamics could produce. Astronomers immediately went looking for the mistake. This is the correct response. The history of astronomy is rich with examples of instruments that found something revolutionary and turned out to have a calibration problem. In 2011, a loose fiber optic cable produced what looked like faster-than-light neutrinos. In 2014, a signal interpreted as primordial gravitational waves turned out to be contamination from foreground dust, inadequately removed from the data. Both errors were caught. Both were caught quickly, because the scientific mechanism for finding systematic errors is robust and well-practiced. Teams applied that mechanism to Webb's early galaxy results. They verified the redshift measurements using 2 independent techniques. Photometric redshift uses color patterns in the light to infer distance and age. Spectroscopic confirmation goes further. measuring the actual emission lines in a galaxy's spectrum, the precise wavelength signatures of individual elements, a direct and unambiguous technique. The spectroscopic campaigns of 2023 took the most extreme candidates from the photometric surveys and ran the harder test on them. The results did not shrink the sample. They confirmed it. The galaxies were real. They were where Webb said they were. They weighed what the photometry indicated. At that point, the question changed. It stopped being whether the instrument was wrong and became what it means that the universe contains. Objects its own history says cannot exist. The problems did not stop with mass. Webb's spectroscopic data revealed a second anomaly layered on top of the first, and this one is, in some ways, harder to explain away. The light from these early galaxies contained chemical fingerprints, spectral lines, the specific wavelengths that individual elements absorb and emit, encode the chemical composition of whatever produced the light. And what Webb read in the spectra of these early structures was not what the first generation of stars should have produced. Carbon, oxygen, iron, these are not primordial elements. The universe began with hydrogen, helium, and trace amounts of lithium. Everything heavier was manufactured inside stars, fused from lighter nuclei over millions of years of nuclear burning, then scattered into the surrounding gas when those stars died in supernova explosions. That scattered material collapsed into the next generation of stars, which were born chemically richer than the first. The process is called nucleosynthesis, and it has a pace that physics fixes and nothing overrides. You cannot inherit a library from grandparents who have not yet been born. The chemical complexity Webb detected in these early galaxies requires stellar ancestors, multiple generations of stars that lived complete lives before the galaxies Webb was observing had time to form, which means the universe needed to complete multiple full cycles of stellar birth, death, and chemical enrichment inside a window the standard timeline barely had room for. 1.2 Independent observational signatures, mass and chemical complexity, each measured by different instruments using different techniques, both pointing at the same broken variable. Not enough time. If the timeline is wrong in the early universe, it was wrong before Webb looked. For decades, we operated with a timeline that may have been telling us something systematically false about the early history of the cosmos then. There is the expansion rate. There is a number that describes how fast space is growing, how quickly the distance between any 2 points in the universe increases with time. This number is called the Hubble constant. For most of modern cosmological history, pinning it down precisely was considered the field's central practical challenge, not because the concept was unclear, but because measuring it accurately enough to matter required instruments that did not yet exist. Two different methods were refined in parallel. The Planck satellite measured the expansion rate from the cosmic microwave background, the thermal relic of the early universe, and arrived at 67.4 kilometers per second per mech. The distance ladder method, using Kifid variable stars and Type 1a supernova as calibrated standard candles, arrived at 73.9% apart. Both measurements internally consistent, both independently verified, both running on the same underlying physics, producing numbers that cannot simultaneously be correct if that physics is one coherent thing. In 2019, Adam Rees, who shared the Nobel Prize in 2011 for discovering that the expansion of the universe is accelerating, said something that received almost no attention outside the field. The Hubble tension had crossed 5 standard deviations. 5 sigma is, in particle physics, the threshold for declaring a discovery. Rees was not announcing a discovery. He was announcing that the disagreement between two methods of measuring the same fundamental constant had grown too large to attribute to chance. He used a specific phrase: "Something is fundamentally wrong." That was before Webb launched, before Labbie's universe, breaker galaxies, before the dark energy spectroscopic instrument measured 6 million galaxies and found the dark energy driving the expansion, behaving in a way the standard model says it cannot. Rees was describing one crack in 2019. By 2024, there were 4 cracks in 4 different walls of the same building. The field spent a decade trying to close the Hubble tension. Every available approach was tried systematically. Teams rebuilt the Kifid distance ladder from scratch using different anchor stars, different calibration pipelines, different software. The gap survived. Independent groups reanalyzed the Planck cosmic microwave background data with modified assumptions about the primordial power spectrum. Some models shifted the derived numbers slightly, but none closed the gap without creating new inconsistencies elsewhere. Theorists proposed early dark energy, a brief burst of additional energy density in the first 100,000 years of cosmic history that would shift the early universe expansion rate toward the later universe measurement. The models helped at the margins. They did not close the gap, they moved it. In 2023, the team that had spent decades building the distance ladder switched from the Hubble Space Telescope to Webb for their keyfied calibration. Webb is sharper. The measurements got cleaner. The gap sat at the same value it had held for 5 years of increasingly precise refinement. A discrepancy that survives every systematic check. That grows statistically sharper with better instruments. That resists every proposed internal fix, is no longer a measurement problem. It is a physics problem. Something is happening in the space between the early universe and the late universe, in the region where the standard model connects to epochs that apparently do not connect smoothly. Now consider the third anomaly. The dark energy spectroscopic instrument spent 5 years mapping the 3-dimensional positions of 6 million galaxies across cosmic history. That is not a sample. That is a census. DESI was looking for baryon acoustic oscillations, the fossilized imprint of sound waves that moved through the plasma of the early universe and left a characteristic scale in the clustering of matter. This scale works as a standard ruler. Measure it at different distances, at different moments in cosmic history, and you can reconstruct how the universe expanded at each of those moments. A frame-by-frame record. What DESI found when it assembled that record is that the lambda in Lambda-CDM, the cosmological constant, the fixed term in Einstein's equations representing the energy density of empty space, does not behave like a constant. Its effective value shifts across cosmic time, stronger at some epochs, weaker at others. The data published in 2024 across multiple papers by an international collaboration of hundreds of physicists shows a statistical preference for dynamical dark energy, a vacuum energy that evolves rather than sitting fixed throughout cosmic history. The cosmological constant is not a peripheral term. It controls the rate at which the universe expands, and its behavior over trillion-year timescales determines how everything ends. The standard picture assumed a fixed lambda and produced a specific trajectory. The universe expands forever at an accelerating rate. Galaxies drift apart until no light from one can reach another. Stars burn out. Black holes evaporate over incomprehensible timescales. What remains is cold and thermodynamically exhausted, the heat death. That picture required lambda to remain at its current value indefinitely. Lambda is not remaining at its current value. If dark energy grows stronger over time, the trajectory changes to something called the Big Rip. Sufficiently strong dark energy overwhelms every other force in sequence. It tears apart galaxy clusters. then individual galaxies, then solar systems, then planets, then atoms. A universe that does not fade into darkness, but shreds, with the final moments occurring faster than the speed of light can carry a signal from one side of a proton to the other. If dark energy weakens and eventually reverses, expansion slows and turns back, collapse, the Big Crunch, a universe that ends where it began. If dark energy oscillates, the trajectory becomes something no current model can reliably predict. 3 different endings corresponding to 3 different behaviors of one variable. We were writing the final chapter of the universe based on a constant that was not constant. To understand how deeply this cuts, you need to understand what Lambda-CDM actually is. Lambda for the cosmological constant, CDM for cold, dark matter, the invisible mass that provides the gravitational scaffolding on which visible structure forms. Together, they describe a universe that is 5% ordinary matter, 27% dark matter, and 68% dark energy. This is the operating system of modern cosmology, the framework inside which every simulation, every prediction, every statement about the universe's past and future is computed. The model worked so consistently across so many independent observations that the question of whether it was accurately describing reality or simply approximating it very well stopped feeling urgent. The cosmic microwave background power spectrum confirmed it. Galaxy clustering statistics confirmed it. Baryon acoustic oscillations confirmed it. The abundance of light elements confirmed it. Each confirmation reinforced the next, until the line between the model and reality blurred, and then Webb made the request the operating system was not built to handle. Early galaxies at the wrong masses. Lambda-CDM fails. Chemical complexity at the wrong epoch. Lambda-CDM fails. Expansion rate disagreement between early and late universe. Lambda-CDM fails. Each failure alone might be a calibration issue or a modeling gap. Together, they constitute something more specific. They are failures occurring not at the edges of the model's predictions, where new physics is expected and acceptable, but at the predictions the model was most certain about. That is not how measurement errors behave. The fourth anomaly is the one that receives the least discussion, possibly because the implication of taking it seriously is the most structurally uncomfortable. The Hercules Corona Borealis Great Wall is a filamentary structure approximately 10 billion light-years in extent, 10 times larger than the scale above which homogeneity is required. The cosmological principle, the foundational premise embedded in Einstein's field equations before a single observation is made, holds that the universe is smooth and uniform at large scales. Every cosmological equation that produces Lambda-CDM requires this premise. The Great Wall exceeds the scale at which that smoothness is supposed to be guaranteed by a factor of 10. If the cosmological principle is wrong, Lambda-CDM is built on a false foundation. If the cosmological principle is correct, the Great Wall requires an explanation that involves physics absent from every model currently on the table. Now consider what dark energy actually is, or rather, what it is not. The cosmological constant appeared in Einstein's field equations in 1917, added by hand to prevent a static universe from collapsing under its own gravity. When Hubble demonstrated that the universe was expanding, Einstein removed it. When supernova observations in 1998 showed that the expansion was accelerating, it was reintroduced and reinterpreted as the energy density of the quantum vacuum, the irreducible energy that empty space carries. Quantum field theory predicts that the vacuum should have an energy density. Virtual particles pop in and out of existence everywhere in space, each pair briefly borrowing energy from the vacuum before annihilating. The sum of their contributions produces a baseline vacuum energy. Physicists calculated what that energy should be and compared it to the cosmological constant we actually measure. The theoretical prediction is somewhere between 40 and 120 orders of magnitude larger than the observed value. Not a rounding error. The largest discrepancy between theoretical prediction and observational measurement in the history of physics. Physicists called it the vacuum catastrophe. The name is accurate. The solution does not exist. Lambda works in every observation we make. The theory predicting its value is wrong by a factor that dwarfs every other failed prediction in science combined. And now DESI reports that even the observable behavior of Lambda is not what was assumed. Lambda is not an explanation of what drives the universe's expansion. It is a very successful placeholder for something we do not understand at all. In 1953, Fred Hoyle walked into a laboratory at Caltech and made a prediction that had no business being correct. Hoyle was working on the problem of how heavy elements form inside stars. Carbon is the bottleneck. Without it, the chain of nuclear reactions producing oxygen, nitrogen, iron, and everything else in the periodic table cannot proceed. For carbon to form in stellar interiors, 3 helium nuclei must collide and fuse in a 2-step sequence. The probability of this happening under normal stellar conditions is almost impossibly low. Too low to explain the abundance of carbon in the universe. And yet carbon is everywhere. In stars, in planets, in every living thing that has ever existed. Hoyle looked at that fact and worked backward. Carbon exists in abundance. Therefore, the reaction rate must be far higher than the raw probability suggests. Therefore, there must be a nuclear resonance state in the carbon-12 nucleus that dramatically enhances the reaction rate by matching the energy of the incoming helium nuclei. He did not calculate this from quantum mechanics. He inferred it from the fact that we exist. He told the experimentalists at Caltech what energy level to look for. They looked. It was there. Not approximately there. At almost exactly the predicted value. A value derived from no calculation, no prior measurement, no physical theory, derived solely from the premise that we are here, and therefore the universe must permit the chemistry that produced us. This points at something deeper. The carbon resonance is one of 26 fundamental constants that define how reality works. The gravitational constant, the speed of light, the mass of the electron, the strength of the electromagnetic force, the cosmological constant. Change any one of them and the universe loses its capacity to produce complexity. Not some complexity, all of it. Reduce the strong nuclear force by 2% in either direction and protons cannot bind into nuclei. Chemistry stops at hydrogen. No stars, no supernova, no heavy elements, no carbon, no planets, nothing that thinks. Increase the cosmological constant by a factor of a few hundred above. Its observed value, and the universe expands so fast after the initial moment that matter never gravitationally collapses into structures. No galaxies, no stars, nothing. Shift the ratio of the electromagnetic force to gravity by 1 part in 10 to the 40th power and stars either burn through their fuel too fast for planetary life or never ignite at all. 20-6 numbers, each sitting at a value that permits complexity, each apparently unrelated to the others at the level of known physics. And together they form an arrangement that allows stars to burn for billions of years, allows heavy elements to form and scatter and recombine into chemistry, allows that chemistry to build structures capable of asking why the numbers are what they are. 3 explanations have been proposed. Each followed honestly to its conclusion costs you something you probably did not anticipate giving up. The first is the anthropic principle, formalized by Brandon Carter in 1974. We observe a life-permitting universe because only life-permitting universes contain observers. If the constants were different, we would not be here to notice. Logically airtight, also completely empty as an explanation. Saying we observe a life-permitting universe because dead observers do not make observations is like saying you survived the car accident because dead people do not give interviews. True explains nothing about why you survived. Lee Smolin pushed further in 1992. Universes reproduce through black holes. Natural selection favors universes that produce more black holes. Our constants are fine-tuned for black hole production, and life is a side effect. The only version of the fine-tuning explanation with a testable prediction. Whether the prediction holds remains debated. The second explanation requires you to accept that our universe is one of an enormous, possibly infinite number of universes, each with different physical constants drawn from the same inflationary process that produced ours. In a large enough ensemble, every combination gets tried. We live in one that worked, scientifically motivated, mathematically grounded in the inflationary mechanism we accepted to explain the smoothness of the cosmic microwave background, also unverifiable in principle. If other universes exist, they are outside our observable sphere and will remain so permanently. String theory enters this picture at a specific point. String theory was proposed to unify quantum mechanics and general relativity, the two most successful theories in physics, each impeccably tested in its own domain, each mathematically inconsistent with the other. The framework required extra spatial dimensions beyond the three we experience, curled up at scales far below anything we can probe. The geometry of those extra dimensions determines the physical constants of the resulting universe. Different geometries, different constants. The number of possible geometries is approximately 10 to the power of 500, not a placeholder for something large. The result of counting distinct geometrical configurations consistent with the string theory mathematics. 10 to the 500 possible sets of physical laws. Leonard Susskind called this the landscape. Our universe occupies one point in it. The theory does not tell us which point. The theory of everything produced a catalogue. We are somewhere in it. The third explanation is that the constants are not fundamental. A deeper theory will show that their values follow necessarily from underlying mathematics, the way the rules of arithmetic follow from axioms rather than choices. This is the most conservative option, and the one with the least current evidence pointing toward it. What is genuinely strange is that we did not go looking for the multiverse from philosophical preference. The inflationary mechanism was proposed to solve two specific technical problems. The first was the smoothness problem. Regions of the observable universe on opposite sides of the sky have never been in causal contact. They could not have exchanged energy or information to reach thermal equilibrium, and yet they are at the same temperature to 1 part in 100,000. The second was the flatness problem. The geometry of the universe is spatially flat to extraordinary precision, and maintaining that flatness from the earliest moments required the initial energy density to be fine-tuned to 1 part in 10 to the 60th power. Alan Guth proposed in 1981 that in the first tiny fraction of a second the universe expanded exponentially, stretching everything into causal contact before the expansion, then freezing the geometry flat. It worked. The cosmic microwave background confirmed the predictions. Nobody initially asked what inflation does if it does not stop everywhere at once. Andre Linde asked. In 1983, he showed that in most versions of inflationary theory, inflation does not stop globally. It stops locally in patches while continuing in the surrounding regions. Those regions generate new stopping patches. each with slightly different physical properties set by quantum fluctuations at the moment inflation ended locally. The process has no global end. It is self-reproducing and eternal, producing an infinite number of post-inflationary regions, each a separate universe with its own constants, its own values for each of the 26 fundamental numbers. We did not choose the multiverse. We chose inflation. The multiverse came as a mathematical consequence of the mechanism we accepted to explain the smoothness of the sky. If bubble universes are real, they collide. When two expanding bubbles intersect in the inflating background, the collision deposits energy on their shared boundary and leaves a mark, a circular feature in the cosmic microwave background with a specific temperature profile. This is a testable prediction. There is a feature in the cosmic microwave background called the cold spot, located in the direction of the constellation Eridanus. It is a region significantly colder than the average background, large enough and statistically anomalous enough that standard inflationary models produce it by chance in roughly 2% of simulations. 2% is not impossible, but 2% sitting alongside a list of anomalies that each independently fall at the edge of statistical expectation begins to accumulate weight. Several research groups have noted that the cold spot has a specific temperature profile, a central depression surrounded by a ring of relative warmth, consistent with the signature expected from a bubble collision, a neighboring universe that intersected ours in the first instant of cosmic history, depositing its boundary energy on our sky, leaving its fingerprint in a temperature map we have now measured for 30 years. The cold spot has other explanations: a supervoid in the foreground, statistical fluctuation. The debate is not settled. What is settled is that the feature exists, that it is anomalous, and that one of its valid physical explanations is that we are looking at a mark left by contact with another universe. Now consider what a JWST says about the nature of space itself. In 1991, Maldacena showed that a specific theory of gravity in a curved spacetime is mathematically identical, not merely analogous but identical, to a quantum field theory living on the boundary of that spacetime. The correspondence has been verified across thousands of papers over nearly 30 years. What it implies, taken seriously, is that gravity is not fundamental. Spacetime geometry, the curvature that holds galaxies together, bends light, and defines distance, is not a stage on which physics happens. It emerges from physics happening. Space is not a container. It is a consequence. Temperature is real, measurable, and causally effective, but not fundamental. It emerges from the collective behavior of particles and would not exist if you described each particle individually. A JWST suggests space is analogous to temperature, emergent from quantum entanglement between degrees of freedom that do not themselves live in space. In 2010, Mark van Romstonk published a paper containing a thought experiment whose implications have not yet been fully absorbed. Take two quantum systems, A and B, make them maximally entangled. In the JWST framework, this corresponds to a connected spacetime, a geometric bridge between two regions. Now reduce the entanglement. The geometric bridge gets longer, thinner. Reduce entanglement to 0, and the bridge closes. The two regions are no longer geometrically connected. The space between them is not empty. There is no space between them. Remove the entanglement and you do not get distant space. You get no space. The space you are currently occupying is not fundamental. It is a consequence of quantum correlations. Remove those correlations and it stops existing entirely. This connects to a puzzle that occupied Stephen Hawking for 30 years. In 1974, Hawking showed that black holes emit thermal radiation, a quantum effect near the event horizon that slowly carries energy away. Given enough time, the black hole evaporates completely. Thermal radiation is random. It carries no information about what produced it. If everything that falls into a black hole eventually leaves as thermal radiation, the information is gone. Not hidden, destroyed. This violated unitarity, the principle that quantum information is always conserved. The argument ran for 3 decades. The resolution came from the holographic principle. Information is stored on the boundary of the black hole, not in its interior. So when matter crosses the event horizon, the information is encoded in the boundary, not destroyed, and can, in principle, be recovered from the radiation. In 2004, in Dublin, Hawking conceded the point. The universe does not destroy information. The past is, in a precise technical sense, permanent, not accessible, not readable, but not gone. The universe is a system with perfect memory. We do not yet know how to ask it to tell us. The observable universe is a sphere, roughly 93 billion light-years across. Everything we have ever measured sits inside that sphere. Everything outside it is moving away faster than light can return from it. Not because the information does not exist, but because it will never reach us. The boundary is physical, and everything we call cosmology was built from data, collected inside it. The problem is that we did not build our models as if they were local. We built them as if they described everything. We took measurements from inside our observable sphere, extracted what looked like universal laws, and applied those laws to regions we cannot observe and will never observe. Eternal inflation implies our sphere is one patch in a self-reproducing structure with no global edge and no global physics. The 26 constants are what our patch drew when inflation ended here. Other patches drew other values. The laws we measured are the laws of this address, the fine-tuning of the constants, which looks from inside a single universe like extraordinary coincidence, looks from inside an eternal, inflationary multiverse like the straightforward consequence of being inside a patch that permitted the development of observers. What does it mean to do physics knowing the sample size is 1? What does it mean that the foundational assumption of cosmology, that laws discovered locally apply globally, is exactly what inflation's own mathematics undermines? This is the position that data has brought us to. Everything we know about the universe is accurate inside a boundary we cannot cross. Describing a region we have no reason to believe is typical of anything beyond it. Physics has a pattern. When a small anomaly survives every explanation the existing framework can offer, the resolution eventually costs the framework itself. For 50 years, the orbit of Mercury was wrong. Mercury's elliptical orbit rotates slowly after each complete revolution, a phenomenon called perihelion precession. Newtonian mechanics predicts this. But when astronomers subtracted the calculated contributions from planetary perturbations, a residual remained, 43 arc-seconds per century. Too small to see without instruments built specifically for it. For 50 years, that number sat in the literature without a theoretical home. Proposals accumulated. An undiscovered planet interior to Mercury's orbit, called Vulcan. Searches were conducted. Vulcan was not found. A slight flattening of the Sun. Measurements were attempted. The Sun is round enough. Every explanation within the Newtonian framework produced at least one additional problem. The number just sat there. In 1915, Einstein completed general relativity. One of his first calculations was Mercury's perihelion precession. The result was 43 arc-seconds per century, exactly, without free parameters, without adjustment. The number that had been theoretically homeless for 50 years fell directly out of a theory, built on completely different conceptual foundations. Not modified Newtonian gravity, not a correction to the existing framework. a reconceptualization of what gravity is. The cost of explaining 43 arc-seconds was Newtonian mechanics. The Hubble tension is 9%, 2 orders of magnitude larger. The early galaxy problem, the DESI dark energy result, and the Great Wall are all theoretically homeless right now, in precisely the position Mercury's precession occupied in 1870. It took 50 years to close a 43 arc-second gap. The current gaps are larger, and there are 4 of them. 3 broad directions exist for whatever comes after Lambda-CDM. None has won. The first modifies gravity. Modified Newtonian dynamics and its relativistic descendants attempt to reproduce Lambda-CDM's observational successes without invoking dark matter. They produce some successes. They struggle with observations of colliding galaxy clusters, where the mass distribution clearly separates from the visible matter in ways modified gravity cannot cleanly reproduce. The second direction keeps the general framework and adds ingredients. Early dark energy shifts the cosmic microwave background-derived expansion rate slightly, reducing the Hubble tension at the margins. Every added ingredient solves one problem and creates pressure somewhere else. The third replaces the substrate entirely. Loop quantum cosmology replaces the Big Bang singularity with a quantum bounce. Causal set theory replaces the continuous spacetime of general relativity with a discrete structure at the Planck scale. Not adjustments to the standard model, but replacements for the spacetime manifold on which the standard model is written. These approaches are not yet complete enough to make the full range of cosmological predictions at the precision Lambda-CDM achieves. Each direction looks promising until it meets the full dataset. Whatever comes next is probably not an extension of any of these 3 directions. The resolution, when it arrives, is more likely to come from outside the current framework entirely. There is something else Webb has brought into sharper focus. A question that Enrico Fermi asked over lunch at Los Alamos in the summer of 1950. The galaxy is old enough and large enough that if intelligence arises with any meaningful probability, it should by now be visibly populated. The sky is silent. Frank Drake formalized this in an equation in 1961. Star formation rate, fraction with planets, fraction with habitable conditions, probability of life arising, probability of intelligence emerging, probability of technology developing, average lifespan of a transmitting civilization. Multiply the factors together and you get the number of detectable civilizations. Webb is now measuring some of those factors directly. Kepler data puts planetary system frequency very high. Most sun-like stars have planets, with roughly 1 in 5 hosting something in the habitable zone. Webb detected water vapor, carbon dioxide, and sulfur dioxide in the atmospheres of exoplanets. Every factor Webb can measure has moved the equation toward a larger answer. Every factor Webb cannot measure, whether life actually arises, whether intelligence survives long enough to transmit, carries all the explanatory weight for why the answer is apparently 0. Robin Hansen published a paper in 1998 called The Great Filter. Whatever process is responsible for the cosmic silence, whatever step between the conditions for life and the evidence of intelligence is so improbable that the galaxy is empty despite being old enough to be full, is the filter. The question is not whether the filter exists. The silence requires one. The question is where it sits relative to where we are. If the filter is behind us, the hard step is something in our past, the origin of life, the emergence of complex cells, the evolution of intelligence. We are among the rare successes. If the filter is ahead, most life that reaches our stage does not survive what comes next. We are not a rare beginning. We are a typical civilization approaching a typical end. Makes Webb's contributions to this question particularly pointed is that every planet Webb confirms as potentially habitable increases the number of civilizations that should have reached our stage. The more habitable the universe appears, the worse the silence becomes, and the more the filter must concentrate its effects in the territory no telescope can measure. Consider where all of this leaves us. Step 1. Copernicus in 1543. Earth moves. The resistance was not simply theological. Accepting heliocentrism meant accepting that our location was not privileged. What followed was Newtonian mechanics, the first mathematical description of the cosmos as a unified physical system. Step 2. Hubble in The Milky Way is one galaxy among roughly 2 trillion. What followed was the expanding universe, the Big Bang, the whole architecture of modern cosmology. Step 3. The cosmological principle. We occupy no preferred location in a homogeneous and isotropic universe. What followed was Lambda-CDM, 30 years of precision cosmology, the operating system of modern science. Step 4 is happening now. Our laws are not universal. They are local. The physics we measured inside our observable sphere may not hold beyond it. Each time physics has acknowledged that our position is less central than assumed. What followed was an expansion of what could be understood. The data forced each of the previous 3 steps. The data forcing step 4 is already in. Start from what Webb showed us and follow the chain without stopping. Webb found galaxies the standard timeline cannot explain. That timeline runs on Lambda-CDM. Lambda-CDM depends on a cosmological constant the 6 million galaxies show is not constant. A drifting constant means the vacuum energy is dynamical. Quantum field theory predicts the vacuum energy should be 120 orders of magnitude larger than what we measure. The largest failed prediction in physics. The 26 constants are tuned with a precision random chance cannot produce in a single universe. Explaining them requires either an infinite ensemble of universes, which falls out of the inflationary theory we accepted to explain the smooth cosmic microwave background, or a deeper theory that nobody has found yet. If the ensemble is real, our constants are local. Local constants mean local laws. Local laws are consistent with the holographic principle. That is consistent with a JWST. Gravity emerges from quantum physics on a boundary. Emergent gravity is consistent with Van Rom's. Space-time conductivity is a consequence of quantum entanglement. Remove the entanglement, space stops existing. Every link in that chain holds. The chain ends not at an answer but at a boundary, the limit of what physics can currently say. The statement, "This is not our universe," does not mean the universe is wrong or alien or broken. It means the universe we described was a local description that we extended globally without the evidence to justify that extension. Our observable sphere is the inner tank. Webb is the first instrument sensitive enough to notice that some of what we see in it is behaving in ways the inner tanks. Chemistry cannot explain. What does it? Mean that space is not a container but a consequence of quantum correlations? What does it mean that the laws we measured with such precision turn out to be the laws of this address, and not necessarily the laws of the full structure? What does it mean that the foundational assumption of all of modern cosmology, that physics discovered locally applies everywhere, is exactly what inflation's own mathematics calls into question? Here is what research looks like at this boundary. Webb will continue observing until at least 2041. The launch was precise enough to conserve more fuel than required, and each year of additional operation extends the return on a $10 billion investment. Every observation cycle brings new data on early galaxy formation, atmospheric chemistry on exoplanets, and the large-scale structure of the cosmic web. Each result will either tighten the existing anomalies or add new ones. The dark energy spectroscopic instrument will continue accumulating its galaxy sensors, refining the measurement of dark energy's behavior across cosmic time and either confirming or constraining the drift. It reported in 2024, if dark energy is genuinely dynamical, future surveys will begin to reveal the shape of that evolution. Theoretical physics is working in parallel. Loop quantum cosmology is developing tools to make precision predictions that can be compared against the cosmic microwave background power spectrum. Causal set theory is building the computational infrastructure to model large-scale structure from discrete space-time foundations. These are slow, painstaking programs, but they represent genuine attempts to replace the substrate rather than patch the framework. The holographic principle and ADS-CDM continue to generate results in theoretical physics that are reshaping how physicists think about the nature of space, time, and information. The resolution of the black hole information paradox, achieved through decades of work connecting holography to quantum mechanics, demonstrated that deep structural questions can be resolved when the right framework is found. Physicists working on emergent gravity and emergent spacetime believe the same pattern may apply at the cosmological scale. What scientists do not yet know is which of these directions will ultimately produce a successor to Lambda-CDM that closes all four of the current anomalies simultaneously. No existing approach manages that. Every modification to gravity succeeds in some areas and struggles in others. Every attempt to add ingredients to Lambda-CDM redistributes the tension rather than eliminating it. Every foundational replacement remains incomplete at the level of observational precision the current data demands. The gap between the old answer and the new answer is real, and it has not yet been filled. What is happening right now is genuinely unusual in the history of science. We are not before a revolution, unaware that one is coming. We are inside the uncertainty, with enough understanding to see the shape of the problem clearly, and not yet enough to see the shape of the answer. The anomalies are accumulating in real time. The field's response is the careful language of physicists who do not know what to do yet. Unexpected, difficult to reconcile, challenging our current understanding, which is how physics sounds when reality is telling it something the model said could not be true. There is a structure buried in the history of these discoveries that is worth naming directly. In 1543, Copernicus published, "The resistance was the recognition that accepting heliocentrism meant accepting something larger, that Earth was not special, that our location was not privileged." Each time that realization has repeated itself in science. What followed was new understanding that could not have been built on the old assumption. The pattern is not accidental. Every time physics acknowledged that our position is less central, what followed was an expansion of what could be understood. You are living through the fourth iteration of that pattern. At this magnification, the universe itself is the house. What it sits inside is the question the zoom has opened. What step 4 produces the way the previous 3 produced? Newtonian mechanics and the cosmic microwave background power spectrum is not yet known, but the data forcing step 4 is already in. The telescope is still looking, the data is still arriving, and the silence where the answer should be is getting louder, not quieter. If you find yourself thinking carefully about these questions, following the data wherever it leads, and willing to sit with the discomfort of not yet having the resolution, that instinct is the right one. The scientific community working on these problems needs more careful thinkers tracking the observations, the theoretical proposals, and the accumulating evidence. Like this video, subscribe so you do not miss the next one, because the next round of web data is already being analyzed, and the picture it builds may clarify the question or deepen it in directions nobody has anticipated. The universe produced something capable of noticing that it does not understand the universe. What we do now that we have seen enough to know the answer is not yet, is the most interesting question in physics. To understand the full weight of what Webb has revealed, it helps to step back and trace how the standard model of cosmology was constructed in the first place. Because only by understanding how carefully and incrementally the foundation was built can you grasp what it means when the structure built on top of it begins to show stress. The cosmic microwave background. The thermal relic Mather spent his career measuring was first detected accidentally in 1965 by Arno Penzias and Robert Wilson at Bell Labs. They were working on a microwave antenna and kept picking up a faint, uniform noise that seemed to come from every direction in the sky simultaneously. They checked for instrument malfunction. They removed a nest of pigeons from the antenna and cleaned the equipment. The noise persisted. A few kilometers away at Princeton, Robert Dicke and his team had independently predicted that if the early universe was hot and dense, as the Big Bang model suggested, it should have cooled enough by now to leave a detectable thermal afterglow at microwave frequencies. When Penzias and Wilson published their result, the two groups realized simultaneously what they were looking at. The cosmic microwave background was the first direct evidence that the early universe was once a hot, dense plasma, that it cooled as it expanded, and that the light trapped inside that plasma was eventually released when atoms formed, and the universe became transparent for the first time. It was also the first observational confirmation of the Big Bang model as a real physical history rather than a mathematical convenience. What Mather and his COBE team did in the 1990s was take that confirmation to a new level of precision. The cosmic microwave background is not perfectly smooth. It has temperature variations at the level of 1 part in 100,000, and the pattern of those variations encodes an extraordinary amount of information about the early universe. The shape of the pattern, the relative strength of fluctuations at different angular scales, is a precise prediction of the theoretical model. COBE found those fluctuations at exactly the right amplitude and distribution. The subsequent WMAP satellite refined the measurement further, and the Planck satellite refined it to extraordinary precision. At every step, the data confirmed the model. This is the context in which Mather's 4 words carry their weight. He is not an outside critic pointing at the edifice from a distance. He measured the bricks, certified the mortar, signed off on the specifications, and then looked at what Webb was showing him and said, "The building is not what he certified." The calibration of Webb itself is worth spending time on, because the history of astronomy includes too many cases where a revolutionary result turned out to be an instrumental artifact. The Michelson-Morley experiment, the gravitational wave detection that turned out to be contaminated by correlations in the 2 detectors, the faster-than-light neutrinos from a loose cable, the BIS PP to gravitational wave signal from inadequately subtracted dust. Each of these produced extraordinary headlines and then quietly retracted when the systematic error was found. Webb's early galaxy results went through the same scrutiny. The telescope was calibrated against multiple independent standards before launch and recalibrated in orbit. The redshift measurements, which establish both the distance and the look-back time of a galaxy, were verified using 2 methodologically distinct techniques. Photometric redshift uses the characteristic color pattern of galaxies to infer their distance, a technique that is powerful but depends on spectral templates and assumptions about galaxy types. Spectroscopic confirmation goes directly to the emission and absorption lines of individual elements in the light, measuring the actual wavelengths of known atomic transitions and calculating redshift from the shift in those lines. These 2 techniques are independent at the instrumental level and at the theoretical level. When they agree, the agreement is meaningful. The 2023 spectroscopic campaigns took the most extreme candidates from the photometric surveys and applied the harder, more direct test. Every door that could have admitted a systematic error was tested. None of them were open. The history of cosmological measurements is also a story about how the community's confidence in its instruments was earned slowly over decades. The Hubble Space Telescope, when it was first launched in 1990, had a spherical aberration in its primary mirror caused by a flaw in the testing process on the ground. The mirror was perfect to the specifications that had been incorrectly set. The corrective optics installed during a servicing mission in 1993 restored the telescope's vision and launched an era of precision cosmological measurement. The cosmic microwave background experiments went through multiple generations of refinement, from COBE to WMAP to each generation tightening the measurements and each time confirming the same underlying picture. Webb was built with this entire history in mind. The calibration protocols were designed around the lessons from every previous instrument. The verification campaign after launch was thorough. The community's confidence in the results is not naive enthusiasm. It is earned skepticism that looked for the mistake and did not find it. Now consider the landscape of observational cosmology and how the anomalies cluster. The galaxy two-point correlation function describes how galaxies cluster at different scales. At the largest scales, the standard model predicts a specific pattern of clustering. Several surveys have found that the observed clustering is subtly different from predictions in ways that are individually within uncertainty but collectively consistent with something the model is not capturing. The matter-power spectrum, the distribution of matter density fluctuations at different length scales, shows tensions between measurements derived from the cosmic microwave background and measurements made directly from galaxy surveys. The sigma-8 tension, referring to a specific parameter describing the amplitude of matter fluctuations, has persisted across multiple surveys and multiple analysis approaches. Each of these is smaller than the Hubble tension. Each has been argued about, modeled, and none has been resolved in the direction of the model being confirmed. They accumulate not as decisive refutations, but as a pattern of the model consistently underperforming in the direction of predicting too much coherence in the early universe and too little variation in the late universe. The kilodegree survey, the dark energy survey, and the South Pole telescope have all contributed measurements that sit in mild tension with Lambda-CDM predictions. The Atacama Cosmology telescope results tightened the measurements further. In each case, the tension is below the 5 sigma threshold that would constitute a definitive anomaly in isolation. In combination, they sketch the outline of a framework that fits its own era of calibration data precisely and then begins to strain when applied to independent data from different epochs and different scales. This is a pattern that physicists recognize. A theory that was fitted to a specific class of observations often performs well within that class and begins to show residuals when pushed outside it. The residuals are not proof of failure, but they are the first signals that the theory's regime of validity may be narrower than assumed. Lambda-CDM was calibrated against the cosmic microwave background, the large-scale structure of the universe at redshifts below 2, and the expansion history traced by Type 1a supernova. Webb is probing redshifts of 5, 8, 10, 12. It is operating in a regime where the model was extrapolated rather than tested, and the extrapolation is not holding the nucleosynthesis. Constraints on the early universe offer another window into these tensions. Big Bang nucleosynthesis, the process by which hydrogen, helium, and lithium were forged in the first few minutes of cosmic history, is one of the model's most precise predictions. The predicted abundances of helium and deuterium as fractions of total hydrogen agree with observations at the few percent level. This agreement is often cited as one of Lambda-CDM's great successes, but the lithium problem is a persistent thorn. The predicted primordial abundance of lithium-7 is roughly 3 times higher than what is actually observed in the oldest, most metal-poor stars. This discrepancy has been known for decades and has resisted every proposed solution within the standard framework. Nuclear physics uncertainties, stellar depletion mechanisms, and various non-standard models have all been invoked. None provides a clean resolution. The lithium problem is small enough that it does not threaten the framework by itself, but it sits alongside the Hubble tension, the early galaxy problem, the DESI result, and the Great Wall as another member of a family of anomalies that the framework was not designed to accommodate. Consider what nucleosynthesis itself tells us about the universe's earliest moments. In the first 3 minutes after the Big Bang, the universe was hot enough and dense enough for nuclear reactions to proceed. Protons and neutrons combined into light nuclei at rates determined by the temperature, the density, and the fundamental constants, the fractions that emerged, about 75% hydrogen and 25% helium by mass, with trace amounts of deuterium and lithium, depend sensitively on the values of those constants. If the gravitational constant were slightly different, the expansion rate during nucleosynthesis would change, altering the temperature at which reactions froze out and producing different elemental abundances. If the strong nuclear force was slightly different, the binding energies of nuclei would change, altering which reactions were energetically favorable. The agreement between predicted and observed primordial abundances is one of the strongest constraints on the fine-tuning of the constants. It is also, in a deeper sense, evidence that the constants we measure locally held the same values during the first 3 minutes of cosmic history. If the constants are local, as the multiverse scenario implies, they presumably settled to their current values during or immediately after inflation, well before nucleosynthesis. But if they can drift over cosmic time, as DESI's dark energy result hints, the question of whether they have drifted enough over the age of the universe to affect nucleosynthesis becomes alive. 1. There is a community of physicists who study variations in the fundamental constants over cosmic time, testing whether the fine structure constant or the proton-to-electron mass ratio have changed since the early universe by examining atomic transitions in quasar absorption spectra. The results to date are consistent with no variation at the precision achievable. But the precision is not unlimited, and the measurements cover only a fraction of cosmic history. Whether the constants are truly fixed, or whether they can evolve on cosmological timescales, remains an open question that intersects directly with the dark energy problem. The holographic principle deserves deeper exploration, because its implications reach further than most popular discussions. Acknowledge, the original insight came from Jacob Bekenstein's analysis of black hole thermodynamics in the 1970s. The entropy of a black hole, its information content, is proportional to the area of its event horizon, not its volume. This is counterintuitive. For ordinary objects, the amount of information needed to describe them grows with their volume. A box of gas twice as large contains twice the volume of space and can hold correspondingly more information. A black hole does not behave this way. Double the mass and you quadruple the event horizon area, not double it. The information scales with area, not volume. Hawking's calculation of black hole radiation reinforced this. The thermal radiation a black hole emits carries entropy outward, and the entropy bookkeeping only closes if the information is stored on the surface. Bekenstein and Hawking had found, by trying to reconcile thermodynamics with general relativity and quantum mechanics, that the maximum information content of any region of space is bounded by the area of the surface surrounding it, not the volume it contains. This is the holographic bound. It applies not just to black holes, but to any region of space. The observable universe has a surface, the cosmological horizon, the boundary beyond which light cannot reach us. The holographic bound implies that the maximum information content of the observable universe is finite and determined by the area of that horizon. Everything inside, every galaxy, every particle, every interaction, is in some sense encoded on that surface. Maldaceno's ADS-CFT result made this precise in a specific theoretical context. Anti-de Sitter space is a spacetime with negative cosmological constant, which curves in a specific way that makes the mathematics tractable. The conformal field theory living on its boundary is a quantum theory without gravity. Maldaceno showed that these two descriptions are completely equivalent. Every process in the interior bulk, spacetime with gravity, corresponds to a process in the boundary theory without gravity. The two descriptions contain exactly the same information. What this means is that gravity, spacetime, curvature, and the three spatial dimensions of the bulk are all redundant. They are a different description of the same physics that the boundary theory encodes without them. Spacetime geometry is not fundamental. It is emergent. It is one way of describing a quantum system that can also be described without invoking geometry at all. The challenge is that our universe has a positive cosmological constant, not a negative one. It is de Sitter space, not anti-de Sitter space. A DSCFT does not directly apply to our universe, and finding the DSCI analog of a DSCFT has proven extremely difficult. Theoretical work continues on this problem, and progress has been made, but a complete de Sitter holography has not yet been achieved. The gap between the theoretical framework and the actual universe we inhabit is real and actively being worked on. Nevertheless, the general lessons of holography have percolated through theoretical physics in ways that are reshaping foundational thinking. If spacetime is emergent in anti-de Sitter space, it is at least plausible that it is emergent in our universe as well. If information is fundamentally on surfaces rather than in volumes, the way we think about what the universe contains, what is fundamental and what is derived, needs to change. Van Romstank's thought experiment made the quantum mechanical foundation of this explicit. The geometric connection between two regions of spacetime is not a fixed background structure. It is a consequence of the quantum entanglement between the degrees of freedom in those regions. Change the entanglement and you change the geometry. This connects directly to the black hole information paradox in a way that goes beyond the holographic resolution. If spacetime connectivity is a consequence of entanglement, then the question of what happens to the geometry when matter falls into a black hole becomes the question of what happens to the entanglement structure when quantum information crosses the horizon. The firewall paradox, proposed by Ahmed Almhiri, Donald Maroff, Joseph Polchinski, and James Sully in 2012, sharpened the tension between unitarity, the equivalence principle, and low-energy field theory outside black holes to the point of apparent contradiction. An infalling observer, according to general relativity, should experience nothing unusual at the horizon, smooth spacetime, the equivalence principle intact. But if information is to be preserved and the radiation is to carry it out, the radiation must be entangled with the early radiation already emitted. This means the infalling observer cannot also be entangled with the interior of the black hole, because quantum mechanics forbids maximal entanglement with two different systems simultaneously. The implication, carried through the logic, is that the infalling observer hits a wall of high-energy radiation at the horizon rather than smooth spacetime. The firewall paradox revealed that something has to give, either unitarity or the equivalence principle, or low energy field theory outside horizons. All three cannot simultaneously hold. The resolution likely requires understanding spacetime in a fundamentally new way, and the research programs following from holography, from ER equals EPR, from quantum error correction models of holography, are all attempts to find the language in which the resolution can be expressed. R equals EPR is a proposal by Juan Maldacena and Leonard Susskind from 2013. ER refers to Einstein-Rosen bridges, the geometric connections through spacetime, also known as wormholes. EPR refers to the Einstein-Podolsky-Rosen paradox about quantum entanglement. The proposal states that whenever two quantum systems are maximally entangled, they are connected by a non-traversable Einstein-Rosen bridge. Entanglement is geometry. Quantum correlations between particles are geometric connections through spacetime. The two phenomena, long thought to be unrelated, may be two descriptions of the same underlying structure. If E equals EPR is correct, then the entanglement structure of the quantum vacuum determines the geometry of spacetime at every scale. The smooth spacetime we observe is the large-scale average of a vast web of quantum connections between degrees of freedom at the Planck scale. Remove those connections, and the smooth geometry dissolves. This is what Van Romsdank's thought experiment demonstrates. The geometry is the entanglement. Changing one changes the other. What does this mean for cosmology? It means that the Big Bang, the singularity where general relativity breaks down and all known physics reaches its limit, is potentially reframed as a moment when the entanglement structure of the universe was radically different from what it is now. Loop quantum cosmology replaces the singularity with a quantum bounce, precisely by modifying the structure of spacetime at the Planck scale, where quantum effects dominate. If spacetime is emergent from quantum entanglement, then the bounce can be understood as a reorganization of that entanglement structure through the extreme conditions of the Big Bang moment. This connects to the question of what preceded the Big Bang. In standard Lambda-CDM, the question is time began at the singularity. There is no before. In inflationary models, the situation is more complex because inflation implies an eternally inflating background that extends infinitely into the past. In loop quantum cosmology, the quantum bounce implies that a previous contracting phase existed before the bounce, with its own cosmological history. In string theory cosmologies involving collisions between higher dimensional brains, the Big Bang is the moment two brains collided, and the pre-collision history extends indefinitely. Webb cannot resolve which of these is correct, but the anomalies it has found in the early universe are beginning to constrain the options in ways that were not possible before. The chemical abundances in early galaxies constrain models of the first stellar populations and their lifetimes. The masses and distribution of early galaxies constrain the rate and efficiency of structure formation. As these constraints accumulate, they will begin to distinguish between models that make similar predictions for the late universe but differ in their implications. For the early universe, one of the most scientifically productive aspects of the current anomaly accumulation is that it is happening at a time when the community has the theoretical tools to take the implications seriously. The development of holography, the progress in loop quantum cosmology, the advances in lattice quantum chromodynamics that allow precision calculations of nuclear properties from first principles, the growing toolkit of numerical relativity. All of these make it possible to engage with the anomalies more rigorously than would have been possible even 20 years ago. The string theory landscape, for all its theoretical challenges, has produced a deeper understanding of how the relationship between higher dimensional geometry and four-dimensional physics works. The anthropic reasoning that accompanied the landscape, controversial as it is, forced the community to think carefully about the conditions necessary for observers to exist and how those conditions constrain the range of valid theoretical predictions. These are uncomfortable questions, but engaging with them seriously has sharpened the conceptual tools available for thinking about the fine-tuning problem. The multiverse, whether it exists or not, has functioned as a productive theoretical forcing function. If you take seriously the possibility that the constants are not fundamental but are selected from a distribution, you are forced to ask what that distribution looks like, what selects from it, and what predictions differ between a multiverse model and a model with fixed constants. These questions have driven theoretical research that would not have been pursued otherwise, and have produced results that are valuable independent of whether the multiverse is real. The situation in 2026 is that the anomalies have crossed a threshold. They are no longer the kind of discrepancies that patient refinement of measurements and models is expected to resolve. They are the kind of discrepancies that require a new idea, not a new parameter, not a refined calibration, but a genuinely new conceptual structure that makes the anomalies comprehensible rather than problematic. The history of physics suggests this is not a disaster, but an opportunity. Every time physics has been forced out of a framework by evidence that the framework could not accommodate, what emerged was a deeper understanding that incorporated the old framework as a special case. Newtonian mechanics is the low-velocity, weak gravity limit of general relativity. Classical mechanics is the large action limit of quantum mechanics. Thermodynamics is the large number limit of statistical mechanics. Whatever comes after Lambda-CDM will incorporate it the same way, applying in the regime it was calibrated for, and extending beyond it in ways that resolve the current anomalies. What we do not yet know is how long this transition will take. Mercury's perihelion took 50 years to find a home in general relativity. The ultraviolet catastrophe, the failure of classical physics to describe the spectrum of radiation emitted by hot objects, was resolved in about 5 years by Planck's quantum hypothesis. The stellar energy problem, the question of what powers the sun, sat unresolved for decades before nuclear physics provided the answer. The pattern of resolution times is not uniform, and does not obviously predict when the current anomalies will find their homes. What Webb is doing in the meantime is building the empirical case with unprecedented precision. Every additional galaxy at unexpected redshift and unexpected mass tightens the constraint on the standard timeline. Every atmospheric spectrum from an exoplanet builds the statistical database on which future claims about biosignatures will be evaluated. Every measurement of the large-scale structure of the early universe refines the constraints on the initial conditions of cosmic history. The telescope is functioning as a discovery machine operating at exactly the boundary where the existing theoretical framework runs out of reliable predictions. The team behind Webb designed it to answer specific questions. How did the first galaxies form? What are the conditions in the atmospheres of planets around other stars? What is the distribution of matter in the early universe? The telescope is answering those questions, and the answers are not what the standard model predicted. That is not a failure of the telescope. It is the telescope doing precisely what science needs instruments to do, probing the regimes where theories make predictions and checking whether those predictions hold. The researchers analyzing Webb's data are doing the same thing. They are not trying to overturn Lambda-CDM for philosophical reasons or because they are dissatisfied with it. They are following the data wherever it leads, because that is the only scientific option available. When the data says something unexpected, you verify it by every means available. You look for alternative explanations within the existing framework, and when those alternatives exhaust themselves, you begin the harder work of constructing a new framework that can accommodate what the data shows. That harder work is beginning now. The anomalies have been verified. The alternative explanations within Lambda-CDM have been systematically explored and found insufficient. The transition from verifying the problem to constructing the solution is underway. It will take time. It will require theoretical breakthroughs that do not yet exist. It will likely require new observational capabilities beyond what Webb provides, probing even earlier epochs of cosmic history and even finer details of the large-scale structure. But the direction is clear. The data is pointing beyond the boundary of the existing framework. The framework's most careful builders are saying so, and the telescope that revealed the problem is still running, still accumulating data, still sending back images of a universe that is turning out to be stranger, deeper, and more surprising than the most precise models built in the last century were able to anticipate. This is where cosmology stands, not at a dead end, but at the edge of a transition whose shape is not yet fully visible. The anomalies are real. The silence in the framework is real. The question that John Mather's 4 words opened is real. What kind of thing is the universe? And what do we do now that we have seen enough to know the answer we had is not the full one? The telescope keeps looking. The data keeps arriving. And the understanding that emerges from this moment will be one of the deepest revisions in the history of human knowledge about what the cosmos actually is. There is a deeper irony buried in the history of Lambda-CDM that is worth examining carefully, because it illuminates exactly why the current moment is so significant. Lambda-CDM was not constructed as a single unified theory by a single team. It accumulated, layer by layer, through decades of observations that each added a new piece to the picture. The Big Bang framework came first, supported by Hubble's 1924 discovery of galactic redshifts and Penzias and Wilson's 1965 detection of the cosmic microwave background. Dark matter entered the picture through Fritz Zwicky's 1933 observations of galaxy clusters, moving too fast for their visible matter to hold together gravitationally, and was cemented by Vera Rubin and Kent Ford's work in the 1970s, showing that the rotation curves of galaxies require an invisible mass component extending far beyond the visible disk. Dark energy entered last, driven by the 1998 supernova results of the teams led by Saul Brian Schmidt and Adam Rees, which showed that the expansion of the universe is not decelerating as gravity should require, but accelerating as though an additional energy component is pushing space apart. Each piece of this framework was added to accommodate observations that the previous version could not explain. Dark matter explained galaxy rotation curves, but was added without a fundamental particle physics theory of what it actually is. Dark energy explained the accelerating expansion, but was described only by a placeholder constant without any mechanism. Lambda-CDM, at its core, is a framework that works extraordinarily well observationally and is almost completely opaque about what its 2 largest components, the 95% of the universe that is dark, actually consist of at a fundamental level. This opacity was tolerable as long as the framework correctly predicted new observations. For 3 decades, it did. Every new survey, every new instrument, every new measurement came back confirming the predictions to higher and higher precision. The community's confidence grew proportionally. By the time Webb launched, Lambda-CDM had achieved the kind of status that Newtonian mechanics held at the end of the 19th century. A framework so precisely confirmed across so many independent observations that the question of whether it might be fundamentally incomplete had come to feel almost impolite. Then the end of a 19th century parallel became exact. At the end of the 1800s, Newtonian mechanics faced two small anomalies that were generally expected to be resolved by minor refinements: the perihelion precession of Mercury and the failure of the Michelson-Morley experiment to detect motion relative to the luminiferous ether. Both were small. Both resisted every proposed explanation within the Newtonian framework. Both turned out to require not a refinement of Newtonian mechanics, but its replacement by something structurally different. General relativity resolved Mercury's precession. Special relativity resolved the ether problem. Neither was a modification of Newton. Both were reconstructions of what space, time, and gravity fundamentally are. The anomalies Webb has revealed, together with the Hubble tension and the DESI dark energy result, are playing the same structural role that Mercury's precession and the Michelson-Morley result played in 1895. They are small enough to dismiss individually, persistent enough to survive every proposed explanation within the existing framework, and precise enough to serve as the empirical anchors for whatever theoretical reconstruction comes next. What makes the current situation potentially more dramatic is the number of anomalies and their apparent convergence on the same underlying issue. The precession of Mercury was one unexplained number. The current anomalies are at least 4, all pointing at the same foundational assumptions of the Standard Model. The Hubble tension points at a breakdown in the consistency between the early and late universe. The early galaxy problem points at a breakdown in the standard timeline of structure formation. The DESI result points at a breakdown in the assumption that the cosmological constant is constant. The Great Wall points at a breakdown in the cosmological principle of homogeneity. 4 separate symptoms pointing at the same patient. A clinician who finds 4 independent symptoms, all pointing at the same organ system, does not treat them as 4 separate diseases. She identifies the common cause. The organ system in this case is the foundational architecture of Lambda-CDM. The common cause has not yet been identified, but the convergence of the symptoms is already diagnostic. One of the most instructive parallels in the history of science is the development of quantum mechanics itself. In the early 1900s, classical physics faced a series of unexplained phenomena: the ultraviolet catastrophe in blackbody radiation, the photoelectric effect, the stability of atoms, which classical electromagnetism predicted should rapidly collapse as electrons radiated energy and spiraled into the nucleus. The discrete spectral lines of hydrogen and other elements, each anomaly was individually puzzling. Together they formed a pattern that classical physics could not accommodate. The resolution did not come from patching classical mechanics. It came from recognizing that the underlying description of physical reality at small scales was fundamentally different from the classical picture. Energy was quantized. Measurement disturbed the systems being measured. Particles had wave-like properties. The new framework, quantum mechanics, incorporated the old one as the limit in which quantum effects are negligible, which is the limit of ordinary everyday experience. Classical mechanics is not wrong. It is incomplete. It is the approximate description appropriate for the scales at which it was developed. Lambda-CDM will almost certainly occupy the same position relative to whatever comes next. It will be revealed as the accurate description appropriate for the scales and epochs in which it was developed and tested, and the new framework will incorporate it as a limiting case while extending the description into the regimes where Lambda-CDM fails. The question of what that new framework looks like has been a subject of theoretical speculation for decades, and the current anomalies are beginning to constrain the speculation in productive ways. One of the most intriguing theoretical directions involves the possibility that the universe is not four-dimensional at the deepest level. extra dimensions, compact and curled up at scales far below anything we can probe directly, appear in string theory and in various attempts to unify gravity with the other forces. The geometry of those extra dimensions determines the effective four-dimensional constants we measure. If the constants are not fundamental but are determined by geometry, then the fine-tuning problem transforms into a geometry selection problem. Why does the universe have the particular extra-dimensional geometry that produces the constants we observe? String theory's answer, the landscape, is that the geometry is one of an enormous number of possibilities, and we observe the one we observe because it permits observers. This is the multiverse argument again, arriving from a different theoretical direction. What is notable is that both the inflationary multiverse and the string landscape arrive at the same conclusion through independent reasoning. Inflation, which was proposed to solve the horizon and flatness problems, produces eternal inflation and an infinite number of post-inflationary patches as a side effect of its most generic implementations. String theory, which was proposed to unify gravity and quantum mechanics, produces an enormous number of possible vacuum states as a direct mathematical consequence of the number of possible extra-dimensional geometries. 2. Independent theoretical programs, motivated by different observational problems, producing the same theoretical structure. This convergence is either deeply meaningful or a sign that theorists are being led into a shared blind alley. Distinguishing between those possibilities is one of the central challenges of fundamental physics in the coming decades. The observational approach to testing multiverse ideas is extremely limited but not completely absent. If our universe underwent a bubble nucleation event from a parent de Sitter vacuum, and if other bubble universes formed in the same inflationary background, some of those bubbles may have intersected ours in the very early universe. The signatures of such collisions in the cosmic microwave background, circular features with specific temperature profiles, are in principle detectable and have been searched for. The cold spot in the cosmic microwave background remains a candidate, though not a confirmed signature. Future cosmic microwave background experiments with higher sensitivity and better foreground removal may be able to either confirm or rule out the bubble collision. Interpretation of the cold spot, the Simons Observatory, currently under construction, and the proposed CMBs for experiment would both improve on Planck's sensitivity significantly. Whether they find a confirmed bubble collision signature or definitively exclude it, the result will be scientifically valuable. Confirmation would be the first observational evidence for the multiverse. Exclusion would tighten the constraints on inflationary models and the bubble nucleation rate that the large-scale structure of the universe offers another observational window into these questions. The distribution of matter on scales of hundreds of millions to billions of light-years carries information about the primordial that seeded structure, formation, and about the evolution of those structures through the subsequent expansion history. Future surveys with instruments like the Square Kilometre Array, the Vera Rubin Observatories, Legacy Survey of Space and Time, and the Euclid Space Telescope will map the large-scale structure with unprecedented breadth and precision. These surveys will measure the baryon acoustic oscillation scale across a wider range of cosmic history than DESI has achieved, testing whether the evolution of dark energy that DESI reported continues in the same direction or changes behavior. They will also measure the growth rate of structure, the rate at which matter clumps together under gravity, which is sensitive to the nature of dark energy, and two modifications of general relativity at cosmological scales. The growth rate measurement is particularly interesting because modified gravity theories and dark energy models often make different predictions for it even when they make similar predictions. For the expansion history, If you can measure both the expansion history and the growth rate independently, you can begin to distinguish between models that fit one but not the other. The current data does not yet have the precision to make this distinction cleanly. The next generation of surveys will. Gravitational wave astronomy has opened an entirely new window on the universe that is only beginning to be exploited for cosmological purposes. The LIGO and Virgo detectors have measured the expansion rate of the universe using binary neutron star mergers as standard sirens, a technique that is independent of the cosmic distance ladder and the cosmic microwave background. The current measurement from gravitational wave standard sirens falls between the two values in tension, which is consistent with both but not yet precise enough to resolve the Hubble tension definitively. As more events are detected and the measurements improve, the gravitational wave expansion rate will either align with one side of the tension or fall in between in a way that suggests both sides are slightly wrong and the correct value is something neither conventional method was measuring precisely: the Einstein telescope and the Cosmic Explorer. Next generation gravitational wave observatories, currently in planning stages, would be sensitive enough to detect binary mergers at cosmological distances and accumulate the statistics needed to make the gravitational wave expansion rate measurement competitive with the conventional methods. If the tension persists to that level of precision, it will be among the most powerful constraints on whatever new physics is responsible. Pulsar timing arrays have recently added another dimension to this picture. Arrays of millisecond pulsars, spinning neutron stars that emit radio pulses with extraordinary regularity, act as a galaxy-scale gravitational wave detector. Gravitational waves passing through the galaxy introduce tiny timing variations in the pulsar signals. Several pulsar timing array collaborations reported in 2020 free evidence for a gravitational wave background at nanohertz frequencies, consistent with a stochastic background from a population of supermassive black hole binary systems throughout the observable universe. This is itself a significant cosmological result. Supermassive black hole binaries form when galaxies merge, which happens throughout cosmic history. The amplitude and spectral shape of the gravitational wave background they produce depend on the merger history of galaxies and the properties of the black holes involved. Comparing the observed background to theoretical predictions constrains models of galaxy formation and black hole growth. Early indications suggest the amplitude of the background may be somewhat higher than the most common models predicted, which is consistent with the broader pattern of early structure being more abundant than the standard model anticipates. The confluence of these independent measurements from gravitational waves, pulsar timing, the cosmic microwave background, galaxy surveys, and Webb's direct imaging of the early universe is exactly what makes the current moment in cosmology distinctive. It is not a single anomaly from a single instrument that might reflect a systematic error. It is a convergence of independent lines of evidence from independent instruments using independent physical principles and arriving at the same region of disagreement with the standard model. Think about what it takes to produce this kind of convergence by accident. You would need each instrument to have its own independent systematic error, all biased in the same direction, all of the same approximate magnitude, all pointing at the same parameter combinations, all undetectable by the extensive cross-checks that every collaboration applies to its data. The probability of that combination of coincidences falls rapidly as the number of independent measurements increases. This is why the scientific community's response has shifted over the past 5 years from cautious skepticism about individual anomalies to something more like resigned acknowledgement that something real is happening. The language in the papers has changed. The Hubble tension is no longer described as a potential systematic effect to be resolved by better measurements. It is described as a genuine tension requiring a theoretical explanation. The early galaxy problem is no longer described as potentially caused by photometric misidentification. It is described as a confirmed observational result that the standard model cannot accommodate. The strange thing about this moment is that we do not know whether we are standing in front of a small correction or the beginning of a completely new chapter in physics. The astronomers who measured the sky before Einstein did not know they were collecting evidence for relativity. The physicists studying black body radiation did not know they were opening the door to quantum mechanics. They only knew one thing: something did not fit. And that is exactly where we are now. A telescope built to look back toward the beginning of time has shown us that the beginning may not have happened exactly the way we imagined. The universe is not refusing to make sense. It is telling us that our current language may not be deep enough to describe it. Maybe Lambda-CDM survives with modifications. Maybe dark energy reveals something completely unexpected. Maybe space, time, and the constants of nature turn out to be consequences of something beneath them that we have not discovered yet. We do not know. And that is the most important part, because every great transformation in science began with this exact feeling, the uncomfortable moment when the evidence was stronger than the explanation. For thousands of years, humanity has looked upward, believing the universe was something we were slowly figuring out. But perhaps the greatest discovery Webb has given us is not an answer. It is the realization that the universe is still far stranger than the theories we built to contain it. Somewhere in the darkness, photons that have traveled for billions of years are still arriving, carrying information from places and times we have never seen before. The telescope is still listening. The universe is still speaking, and for the first time in a long time, we are not